Next, let us consider the phenomenon of the type where we are considering occurrence of events at shorter duration. For example, we will look at a telephone operator's desk, how many telephone calls are received during half an hour period. Suppose we are looking at a traffic at a particular crossing, how many vehicles of a particular kind pass, how many accidents occur there during a 1 hour period, how many people arrive at a ticket counter at a railway reservation counter, how many people enter through a door of a shopping mall during a particular period. If we consider such type of events, they cannot be put into the success failure model or type 1 model, type 2 category, etc. We describe in a slightly different way. So, one thing that we can observe here is that we are observing the events happening over a period of time or a certain area. For example, if we are looking at number of vehicles passing through a certain portion of a road, it could be in space also. For example, we may look at the number of say comets observed in a particular portion of say universe or a galaxy. So, we are looking at observations or occurrences or happenings observed over time, area or space. Okay. So, if we are observing over time, it is the length of the time or time interval, area as a specified unit, space as a specified unit. We can consider them as happening under a Poisson process, provided they satisfy certain assumptions. Provided they satisfy certain assumptions. Let us look at the assumptions. So, the number of outcomes or number of occurrences. So, for convenience we will consider number of occurrences during disjoint time intervals are independent. So, for example, we may consider time from a to a plus h. Suppose on the time scale the time a and a plus h are here. Suppose the time b to b plus k is here. Then how many occurrences are here or how many occurrences are here are immaterial. For example, the number of earthquakes recorded during say year 1900 to 1910 is independent of the number of earthquakes recorded during 2000 to 2009. If we are looking at the number of say accidents occurred in say year 2001 in month of July in a particular city say Kolkata, and we look at the number of accidents occurring in 2009 in the month of say May in Delhi. So, these must be independent. This is the first assumption that we are making here. Now, in place of time interval, one may consider area, one may consider space. So, that means different portions of the area, different portions of the space, etcetera, can be considered. Now, onwards for convenience, we will restrict attention to the phenomena which are observed over time. So, the derivation of the distribution we will do with respect to that, but it is obvious that it can be changed to area or to the space also. The second assumption is that the probability of a single occurrence during a small time interval is proportional to the length of the interval. The third assumption is the probability of more than one occurrence during a small time interval is negligible. Let us look at the physical significance of this. So, if we say an earthquake occurs at a moment, say at 10 a.m. on a particular date in a particular place, then it is highly unlikely that say at 10 past 1 minute past 10 a.m. again there will be an earthquake of the similar nature at the same place. If we are looking at a train accident at 9 o'clock at a particular place, then it is unlikely that at 9 hours and say 30 seconds there is another train accident there. So, this probability is negligible, and the probability of a single occurrence in a small time interval is proportional to the length of the interval. That means, this is something like a rate of occurrence of the event. If we introduce the notation, say x is the number of occurrences in an interval of length t. So, we will denote it by x t. Now, interval of length t can be considered a to a plus t, it may be considered some b to b plus t, etcetera. So, for convenience we will consider the interval from 0 to t. Since we are making the assumption that the number of occurrences in disjoint time intervals are independent, therefore, the starting point does not make any difference. So, the number of occurrences in an interval of length t will be denoted by x t. We are interested in probability that x t is equal to some number say n. Obviously, since it is number of occurrences, n will be able to take values 0, 1, 2 and so on. So, like a geometric distribution, this is an infinite valued probability distribution, and the number of values taken are countably infinite. We will use the notation for probability x t is equal to n as p n t. So, our aim is to derive an expression for p n t under the assumptions 1, 2 and 3. So, under the assumptions 1, 2 and 3, we have p n t is equal to e to the power minus lambda t to the power n by n factorial. Now, before going to the proof of this, let us understand what is this coefficient lambda coming from. So, we made certain assumption here, the probability of a single occurrence during a small time interval is proportional to the length of the interval. That means, we are saying probability of x during a small time interval, which we can write as epsilon or h, probability that there is a single occurrence in the interval of length h is proportional to the length of the interval. So, this is p 1 h is equal to lambda h. So, lambda is the constant of proportionality here. this lambda is reflected here in the expression for probability x t is equal to n. Now, if we make this assumption, then the third assumption can also be expressed in terms of this probability of more than one occurrence. Now, more than one occurrence means probability of x h, a small time interval, is greater than or equal to 2. That means, it is equal to p 2 h plus p 3 h and so on, which we can write as 1 minus p 0 h minus p 1 h. So, the assumption is that this is negligible. So, by negligibility we can express it in terms of O h, which is small order h. This small order h is explained by small o h by h goes to 0 as h goes to 0. For example, h square, this is an O h term. For example, h cube is an O h term. To prove this statement, which gives the probability distribution of the number of occurrences in the interval 0 to t, let us call it statement number 1. To prove this statement, we can make use of the induction process. Now, we will firstly prove it for n is equal to 0 and n is equal to 1, and then we will make assumption for n is equal to k and proceed to n is equal to k plus 1 case. To prove for n is equal to 0, we need to prove p 0 t is equal to e to the power minus lambda t. So, let us consider the derivation of this p 0 t. We consider p 0 t plus h. Now, this means probability of no occurrence during the interval 0 to t plus h. So, if we are looking at the timeline t to t plus h. So, we can consider this as splitting into two portions 0 to t and t to t plus h. If there is no occurrence from 0 to t plus h, it means there is no occurrence here and there is no occurrence here. So, this can be represented as probability of no occurrence during 0 to t. If we consider this as an event, then it is probability of simultaneous occurrence of these two events. No occurrence during t to t plus h. Now, we make use of the first assumption, that is the number of outcomes or occurrences during disjoint time intervals are independent. So, if we look at this event say b 1 and this event as say b 2, then events b 1 and b 2 are independent. So, probability of b 1 intersection b 2 will become probability of b 1 into probability of b 2. Now, what is probability of b 1? No occurrence during 0 to t. So, if we consider the definition of p and t, it is probability of x t is equal to n, then this probability of b 1 is p 0 t, and similarly probability of b 2 is p 0 h, because the interval from t to t plus h is of length h, the starting point does not matter. So, it is probability of no occurrence during an interval of length h. So, now we have the expression p 0 t plus h is equal to p 0 t into p 0 h. Now, we can make use of the assumptions here. We have 1 minus p 0 h minus p 1 h as small o h and p 1 h is equal to lambda h. If we make use of these two statements, we will get p 0 h is equal to 1 minus lambda h minus o h. So, if we substitute this expression here, we get 1 minus lambda h minus O h. So, let us adjust the terms p 0 t plus h minus p 0 t divided by h is equal to minus lambda p 0 t minus O h by h p 0 t. So, if I take the limit as h tends to 0, then the left hand side is p 0 prime t is equal to minus lambda p 0 t, and since O h by h goes to 0, this term vanishes. We are left with a first order linear differential equation for which the solution is p 0 t is equal to c times e to the power minus lambda t, where c is a constant of integration. This can be determined by using some initial conditions, say p 0 0. Now, p 0 0 stands for the probability of no occurrence in an interval of length 0, which must be 1. This means that c must be 1. So, we get p 0 t is equal to e to the power minus lambda t, which is the statement. If we consider 1 with n is equal to 0, we will get e to the power minus lambda t. So, the statement 1 is true for n is equal to 0. In order to prove the statement 1 using induction, we need to prove it for n is equal to 1. So, for n is equal to 1, let us consider p 1 t plus h. So, p 1 t plus h is probability of single occurrence in the interval 0 to t plus h. So, if we say one occurrence in the interval 0 to t plus h, and if we split the interval 0 to t plus h as 0 to t and t to t plus h, then the one occurrence can be either in this interval or in this interval, that is 0 to t or t to t plus h. So, we can express this event as probability of one occurrence in 0 to t and no occurrence in t to t plus h. So, here we are making use of the addition rule or the theorem of total probability plus probability of no occurrence in 0 to t and one occurrence in t to t plus h. Once again, if we make the use of assumption 1, that means the events occurring in disjoint time intervals are independent, then the probability of simultaneous occurrence of this and this is equal to the probability of product of this. That means, it is equal to probability of one occurrence in the interval 0 to t into probability of no occurrence in t to t plus h plus probability of no occurrence in 0 to t into probability of one occurrence in t to t plus h. So, this is equal to, now if we make use of the notation that p and t is equal to probability that x t is equal to n, then using this probability of one occurrence in interval 0 to t is p 1 t, probability of no occurrence in t to t plus h is p 0 h, probability of no occurrence in 0 to t is p 0 t, and probability of one occurrence in t to t plus h is p 1 h. So, if we substitute the expressions for p 0 h, p 1 h and p 0 t, so p 0 h is 1 minus lambda h minus O h from the assumptions, p 0 t we just now proved as e to the power minus lambda t, and P 1 h is lambda h. So, we can express P 1 t plus h minus P 1 t divided by h. This is equal to, in the second term, minus lambda h P 1 t is there. So, h will cancel out and we get minus lambda P 1 t, and here we get lambda e to the power minus lambda t minus O h by h P 1 t. So, if we again take the limit as h tends to 0, we get the left hand side will yield the derivative of P 1 at t. So, we get P 1 prime t is equal to minus lambda P 1 t plus lambda e to the power minus lambda t. If we notice this is again a first order linear differential equation, and therefore, the solution can be obtained easily. This gives P 1 t is equal to lambda t e to the power minus lambda t plus a constant. The constant of integration can be determined using some initial condition, for example, P 1 0. This means probability of a single occurrence in the interval of length 0, which is obviously 0. So, this will give C 1 is equal to 0. So, P 1 t is equal to lambda t e to the power minus lambda t, which is the expression for P and t if we put n is equal to 1 here, that is lambda t into e to the power minus lambda t. So, the statement 1 holds for n is equal to 1. So, assume that it to be true for n less than or equal to k. So, now we need to prove for p k plus 1. So, p k plus 1 t plus h. This is probability of k plus 1 occurrences in the interval 0 to t plus h. If we look at the breakup here, in the interval 0 to t plus h, we have k plus 1 occurrences. Now, this leads to various possibilities. If we have split the interval into 0 to t and t plus h, t to t plus h. So, all the k plus 1 occurrences may be in the interval 0 to t, no occurrence in t to t plus h, one occurrence in the interval 0 to t, or k occurrences in 0 to t and one occurrence in t to t plus h, k minus 1 occurrences in 0 to t and 2 occurrences in t to t plus h, k minus 2, k minus 3 and so on, including no occurrence in 0 to t and all k plus 1 occurrences in the interval t to t plus h. So, we can express this by using the theorem of total probability as probability of k plus 1 occurrences in 0 to t intersection, no occurrences in t to t plus h, plus probability of k occurrences in 0 to t, one occurrence in t to t plus h. Probability of k minus j occurrences in 0 to t and j plus 1 occurrences in t to t plus h, where summation here is from j is equal to 1 to k. this will, for j is equal to 1, this gives k minus 1 occurrences in 0 to t and 1 occurrence 2 occurrences in t to t plus h. Here j is equal to 2 will give you k minus 2 occurrences here and 3 occurrences here. J is equal to k will give no occurrences in 0 to t and k plus 1 occurrences in t to t plus h. So, we have expressed this event k plus 1 occurrences in 0 to t plus h as the sum of these many probabilities. Once again we notice here that in individual probability terms here, it is simultaneous occurrence in two disjoint intervals. So, by making use of the independence, this becomes probability of k plus 1 occurrences in 0 to t into probability of no occurrence in t to t plus h plus probability of k occurrences in 0 to t into probability of 1 occurrence in t to t plus h. Probability of k minus j occurrences in 0 to t into probability of j plus 1 occurrences in t to t plus h. This is equal to, so the first term here is obviously p k plus 1 t into p 0 h plus p k t into p 1 h plus sigma p k minus j t p j plus 1 h, j is equal k equal to j is equal to 1 to k. We substitute the expressions which are known to us. So, this becomes p k plus 1 t, p 0 h is 1 minus lambda h minus o h, plus we made the assumption that the statement 1 is true up to k. So, this becomes e to the power minus lambda t to the power k by k factorial, and p 1 h is lambda h, plus now here j is equal to 1, 2 and so on. So, this is at least p 2 h. Now, we have made the third assumption in a Poisson process, which says that the probability of more than one occurrence is negligible. We had p 2 h plus p 3 h etcetera as o h. So, therefore, all the terms here will be of o h order. So, this becomes sigma p k minus j t. Of course, the expressions for these are available, as we have assumed that it to be true up to n is equal to k. However, we need not write them into o h. So, p k plus 1 t plus h has been expressed as p k plus 1 t into certain term and many other terms. So, we can go for simplification here. P k plus 1 t plus h minus p k plus 1 t divided by h is equal to minus lambda p k plus 1 t plus lambda to the power k plus 1 t to the power k by k factorial e to the power minus lambda t plus o h by h sigma p k minus j t, j is equal to 1 to k minus o h by h p k plus 1 t. So, if we take the limit as h tends to 0, we get the left hand side as the derivative of p k plus 1 t is equal to minus lambda p k plus 1 t this term will be as it is, lambda to the power k plus 1 t to the power k divided by k factorial e to the power minus lambda t. The term OH by H goes to 0. So, this entire term goes to 0 and this term also goes to 0. We are again left with a first order linear differential equation and this can be solved. So, we get p k plus 1 t as lambda t to the power k plus 1 e to the power minus lambda t by k plus 1 factorial plus a constant of integration. If we make use of the initial condition, say p k plus 1 0 is equal to 1, then this yields C 2 is equal to 0. Therefore, the expression for p k plus 1 t is equal to e to the power minus lambda t to the power k plus 1 by k plus 1 factorial, which is the expression for p and t if we put n is equal to k plus 1 here. So, by the principle of mathematical induction, we have proved that the Poisson distribution holds. So, in a Poisson process, the distribution of the number of occurrences in a fixed time interval is called a Poisson distribution. So, this particular distribution that we obtain, this is known as Poisson distribution, and the system that we have described here, that is the occurrences in a particular way, that is the number of occurrences in disjoint time intervals are independent. The probability of a single occurrence in a small time interval is proportional to the length of the interval. The probability of more than one occurrence in a small time interval is negligible. So, this process is called Poisson process, and the distribution of the number of occurrences in a fixed time interval during a Poisson process is called a Poisson distribution. In the next lecture, we will be discussing the characteristics of this distribution, such as its mean, variance, moment generating function, etc. Just to give you an example, suppose customers arrive in a shopping mall at the rate 5 per minute. Okay. What is the probability that no customer came in a 1 minute period? So, this means we are asking for a probability x equal to 1 is equal to 0. So, here lambda is equal to 5 for unit of time is per minute. So, in a 1 minute period, we are having e to the power minus 5, that is e to the power minus lambda t. Suppose we say 2 customers in a 3 minute period. So, if we are considering 3 minute period, then lambda will be equal to 15 or lambda is equal to 5 and t is equal to 3. So, probability of x 3 is equal to 2, that is equal to e to the power minus lambda t square by 2 factorial. So, in a Poisson process, if we know the rate of the occurrence, then we can find out probabilities of various numbers. For example, probability of a certain number of occurrences, less than a certain number of occurrences, etc. So, in the next lecture, we will elaborate further on this. Thank you.